This video we discuss Green's theorem, which allows us to relate line integrals over closed curves to equivalent double integrals over the region inside that closed curve. Specifically, this time we're going to look at the normal form of Green's theorem, which is related to the flux integral of a vector field. We'll briefly review simple closed curves, how those are defined, and simply connected regions. And then we'll talk about the integrals on the left-hand side and the right-hand side of the normal form of Green's theorem and how we can interpret those physically in the case where F is the velocity of some fluid. And then we'll do an example or maybe two examples depending on time constraints. I don't want to go on too long. So basically this video is about the normal form of Green's theorem, what it says, what it means, and then how to apply it. I'm not proving Green's theorem in this video. I'll do that in another video for those students who are interested. But when you're done with this, you'll know what the theorem says, what it means, and how to apply it to solve problems, and how to interpret your answer. Okay, so let's say we've got a field F in the XY plane, and we've got a curve in the plane that looks like this. Let's make it a closed curve. And it's going to be a simple closed curve. We'll review what that means again in a little bit. So I've got a curve like this. It's closed because it starts and ends at the same place. Now, if I want to find the flux of this field through this curve, it's represented by this integral. So I might say the flux of F across the curve C. And that's the integral over C of F dotted with the unit normal that's pointing outward from that curve times a tiny distance traveled along the curve. So that's length along the curve. Okay, and let's get a little bit more specific about this. Let's say our curve C is being traced out in the counterclockwise direction so that it looks like this. And let's zoom in on just one little location, one little point, little part of our curve. So let's say we're interested in that part right there. So I've got a curve that looks like this. As t increases, we're going this way. When we're at this location, our unit tangent vector points in the direction of motion and it's 1 unit long. And the unit normal vector points in the direction that we're turning. Now that was the unit normal that we studied in an earlier chapter. I'm representing that slightly differently this time. I'm calling that n hat star because it's not actually the normal vector that we're interested in when we talk about flux. This is the inward pointing normal vector. Or the inward pointing unit normal vector. And what we want is the outward unit normal. So this n doesn't point that way, it points the opposite direction. But it's also perpendicular to t hat. Okay. Now, if F represents the velocity of some fluid, it's possible that that fluid velocity at this point might look like this. Well, then it's going to have two components. I can write F as the sum of a component that's parallel to t hat. So that would look like that. And the sum of that component and a component that is parallel to n hat. So that vector over there. Now typically we like to draw it so it has the same initial point as n hat. So we'll draw that vector over here instead. So this F dot N, what it's doing for us is it's finding the component of that fluid velocity that is parallel to n hat. And because we're looking at the outward unit normal, this is the part of that velocity that is crossing that curve. It's going from the inside to the outside. Now, if the fluid velocity was pointing this way, so that the fluid was actually going into the curve rather than out of the curve, that dot product would be negative rather than positive. But in general, this is the magnitude of that component, and it's going to be positive if that fluid velocity vector is going outward. It has some outward component. If the component of F parallel to n hat is in the same direction as n hat, and if our field was going this way, so that the velocity's component parallel to n hat was opposite n hat, then that dot product would be negative. So what this is the signed length of the projection of our fluid velocity onto n hat. So it's some measure of how much that fluid is crossing that curve. We're saying the fluid is crossing, or we're saying that that value is positive if the fluid's going from the inside to the outside. We're saying that that dot product will be negative if the fluid is going from the outside to the inside. And we're doing this and we're multiplying that fluid velocity by a tiny length along the curve, and then we're adding that up as we go all the way around the curve. And we're calling that the flux of F across C. Now, if you do that and the flux happens to be positive, that means more fluid is going out than is coming in. If the flux happens to be negative, that means more fluid is going in than is coming out. If the flux is 0, it doesn't necessarily mean that no fluid is going out or in, but it does mean that as much fluid went in as went out, and vice versa. So that's flux. Now, we said this is not the best expression for evaluating something. If we want to evaluate this, we need to tie all of these variables together using the variable t. So we said if we're on this curve, and the curve C is given by r of t with components x of t and y of t. And t goes from a to b, but r x of a r of, or x of a y of a and x of b y of b are the same because it's a closed curve. Then we said this integral can be evaluated this way if we're in the plane. And for Green's theorem, we are in the plane. You want to write your field in terms of t so that you have every x replaced by x of t and every y replaced by y of t. And now you've got that velocity as a function of the parameter t as you're going around the curve. And then n hat times ds has the same magnitude as the speed as r prime of t dt, but it's oriented differently. The x component is y prime and the y component is negative x prime. And that's just because this vector has to be perpendicular to this vector. And because we have oriented our curve counterclockwise like this, that is the outward pointing unit normal from that location. So I can take this written in terms of t and n hat written in terms of t, and the magnitude of n hat was the magnitude of r prime of t dt, and ds has an r prime of t dt in it, that magnitude in it. Those magnitudes will cancel and you'll just have a dt there. But this is the integral that you evaluate instead. So if I want to find a flux integral, I have to write my field in terms of x and y. I need to find y prime and x prime, substitute them into my normal vector, take a dot product, and then evaluate an integral. That's how we do that. Now, so that's our review of flux integrals of vector fields. And again, what it's doing is it's finding that component of the velocity field that is parallel to that outward unit normal, and then it's multiplying it by a tiny length, and then it's adding those together as you go all the way around the curve. That's flux. So we're sort of adding that together. It's just this summary of how much fluid is going out or coming in. If this is positive, more fluid's going out. If this is negative, more fluid's going in. If this is 0, the same amount of fluid is going out as is going in, and vice versa. Okay, so now let's relate this to Green's theorem. In order to relate this to Green's theorem, we need to review these terms pretty quickly. We did it in the last video, so I won't take too much time with it here. A simple curve does not cross itself. So that's simple. This is not simple. This is simple, and this is not simple. It's okay if a curve starts and ends at the same point. It just can't go through a point and then go through that point again and keep going. That's going to be a problem. So this is simple, and this is not simple. Now, a closed curve is a curve that starts and ends at the same point. So these are not closed, and these are closed, because I start here and I end there, or I start there and then I end there. And that's fine. Okay. And then remember what we said about simply connected regions. A simply connected region is a region that has this property. Every simple closed curve in the region contains only points that lie in the region. So that is simply connected. This one isn't. Because any simple closed curve in here, all of the points inside that simple closed curve are still in here. You're saying, but what about like that and that? Well, if it lies in the region, we're not going to accidentally grab any points out there. Now, if the simple closed curve went beyond the region, we would have points outside of the region. But we're not talking about that. We're talking about simple closed curves that lie in the region R. So this one is simply connected. This one's not. Look, there's a simple closed curve. And there are some points inside the simple closed curve that aren't in the region R. So this one's simply connected and this one's not. Now we have the same requirements for the normal form of Green's theorem that we had for the tangential form of Green's theorem. So here's the normal form. And even though they look different, they're actually equivalent to each other. So we want R to be a simply connected region. And we're in the plane with a piecewise smooth boundary C. oriented counterclockwise again. And we want F to be a field where the component functions of F, M and N, have continuous first partials, first partial derivatives, on an open region containing R. So if you've seen this picture before, I'll draw it again for you. There's C, it's piecewise smooth. Piecewise smooth boundary to a simply connected region R, sets this inside. And here's an open region that contains R. F is a field with components M and N N have continuous first partials, or continuous first partial derivatives. Inside that dotted region. So it's inside here, including that region R. So these guys are continuous on the boundary of R and R itself, and just a little bit beyond the boundary. That's all we need. Okay, if all of that is true, then that flux integral that we talked about. So if F is the velocity field of the fluid, this is a measure of how much fluid is going inside the curve, if it's positive, or if it's negative, or going outside, from outside to inside. That's equal to this. Oops. The double integral over R of the partial of M with respect to X plus the partial of N with respect to Y. And I don't know if you recognize that, but if this is our field and I dot it with the del operator, I take the partial of M with respect to X, and then I add the partial of N with respect to Y. That was the definition of divergence. Remember what divergence means. We said earlier that informally, the divergence of F, that's this, is a measure of how much the field spreads out or diverges from a point. So now we see we're taking this divergence, which is a measure of how much a fluid spreads out at this location, and then we're multiplying it by a tiny area piece, and then we're adding all of that up, and that's giving us the flux of F across C. And I think this makes a lot of sense if you think about it, because F, our field F, let's say that F is given by these blue vectors, which I'm about to draw. F is defined everywhere in here. Every point has a vector F associated with it. And what we're saying here is, what I'd like to do is take the component of F that is parallel to the unit normal, the outward unit normal. So here's our curve. There's the unit tangent. There's the unit normal that we're not worried about. Here's the unit normal that we're interested in this time, outward unit normal. We're saying here's our velocity vector. Find the component of that that's parallel to n hat. Count it as positive if it's going outward, count it as negative if it's going inward. So that's what that is. Multiply it by a tiny length, and then add as you go all the way around, and we're saying that's the flux. Over here they're saying, isn't that the same thing as taking this region so I've got some part of this region R. Just going to zoom in on it like this. And let's divide it into a bunch of little rectangles. And then let's just focus on one little rectangle at a time. It's saying take the divergence of that. When you're on this little rectangle, tell me how much fluid is going in versus going out. And then multiply it by the area of that piece. So maybe some of the fluid is coming in, comes in over here, but then it goes out over here. And do that for all of the pieces. Let's think about it. Isn't the fluid that's going out over here on this little piece going into the next one? And isn't the fluid that's going out of this one into the next one and out of this one into the next one? When I take that divergence of F, which is the measure of how much that fluid is diverging from that location, and we're just evaluating the field at some point, x sub I, y sub I. And we're calculating that. And then we're multiplying by a tiny area piece, dx dy. And we're saying if we do that, if we find the divergence at that point, and the divergence at that point, and the divergence at that point, and the divergence of that point, and we keep doing this, eventually I'm going to get to a little square or rectangle on the side of my region. This is my region here. I tried to draw it over here, it didn't work out. I just started drawing it over here instead. So here's my region. Eventually my rectangle is going to be toward the side. And then I'm going to count that flux, and I'm only going to count it once. Over here, I'm counting that flux as positive, but then I count it in the next adjacent rectangle as negative, and then it's positive on this guy, but then it's negative for this guy, and then it's positive for this guy and negative for this guy. So all of the flux in each little rectangle, they're going to cancel on the interior. The only part that's not going to cancel is that one that's just on the edge. So I take the divergence on each little rectangle. I multiply it by the area of those rectangles and I add them together. They're saying that's the same as the flux of that field across the boundary. And I think that makes sense because what goes into one rectangle is going out of the previous rectangle. So now we can interpret a divergence a little bit more formally. It's still pretty informal. it's a little bit more formally. If flux is divergence times area, divergence must be flux per unit area. If curl was, circulation per unit area, divergence is now represented, when we're in the plane, it's represented as flux per unit area. So it's flux in a little rectangle, just like when we were looking at curl in the last one. That was curl in a little rectangle. Okay, so that is the normal form of Green's theorem. It says rather than evaluating this flux integral, which requires finding that piecewise smooth parameterization of the boundary, and finding x prime and y prime, and then substituting them into my normal vector, which I have required to be an outward unit normal, and then taking a dot product and then integrating from A to B. Instead of doing that, so you don't have to do that. Just do this, find the divergence at all of the points on the interior, add them up by taking the double integral over R of the divergence, and that's going to give you the exact same thing as if you had found the flux across the boundary. So somehow, the behavior of this function on the inside of R is completely determined by that flux on the boundary, and vice versa. I always think of like drum heads and things like that. There's something about the behavior of the function on the interior that affects the behavior of the function on the boundary. And there's something about the behavior of the function on the boundary that affects the function on the interior. Now, I know that we're talking about different functions, and that's very sort of hand wavy, I guess. But I think this is very interesting. It says, rather than focusing on this, I can focus on this. And sometimes, maybe I might want to go the other way. Instead of evaluating this double integral, there might be some cases when I would prefer to evaluate this line integral over the boundary instead. For our purposes, though, most of the time the equation is read this way. Instead of evaluating this, I evaluate this, and that tends to be simpler. Okay, so that's the normal form of Green's theorem. And you have the same three conditions from before. We need a simply connected region with a piecewise smooth, counterclockwise oriented boundary, and M and N have to have continuous first partials in an open region containing R. If all three of those hold, then the flux is equal to the double integral of the divergence. Okay, let's do an example. We actually did this, or worked with this field last time. So we had y equals x, y equals x minus, or y equals x squared minus x here. And in the last video, we used the tangential form of Green's theorem to find, let's say, circulation over the boundary. I may have said that that represented force at the time, but now let's say it represents the velocity field of a fluid. Now this time, rather than asking you for flow or circulation around this curve, which is given by this line integral, oops, not across, around. And since it's a closed curve, we could do that. Rather than finding the circulation of the fluid around C, let's say we want the flux. Now, all of the math holds even if this does not represent the velocity field of a fluid. And this holds for any field with the right properties. This is just an interpretation that's easy for us to wrap our minds around. This works for electric fields, all kinds of fields. So it's the flux of the fluid through C or across C. And again, we're counting it as positive when it goes out, and we're counting it as negative when it goes in. Well, the first thing we do is check the conditions of Green's theorem, and we actually did that in the last video. Do we have a simply connected region R? We sure do. Does it have a piecewise smooth boundary C? It sure does, excuse me. And what else do we need? We need it to be oriented counterclockwise. That's the way I drew it, so yep. If it isn't oriented counterclockwise, just multiply the integral by -1 and it'll be oriented counterclockwise. It has to be oriented that way in order for the sign convention that we chose to make sense. So if it's oriented clockwise, it's going to count fluid going in as positive and fluid going out as negative. If it's oriented counterclockwise, it's going to count fluid going out as positive and fluid going in as negative. Actually, either one would be fine. You just want to make sure that you actually know how to interpret that number that you're getting. So we'll require it to be oriented counterclockwise and treat fluid going out as positive. Okay, so we've got a simply connected region, a piecewise smooth boundary, C, oriented counterclockwise, and the components of the field are both polynomials, so we don't have any problems with continuity. M and N have continuous first partial derivatives. On the entire XY plane. So certainly on an open region containing R. Okay, well in that case, we can apply Green's theorem in normal form. So we'll state the formula for Green's theorem in normal form. So Green's theorem in normal form says that flux integral is equal to the double integral over R of the divergence of F dA. And all we need to do to evaluate this is compute the divergence and compute find bounds for the region R. We did that in the last video. We'll do that again here briefly because some people may only be watching this video and not the other one. But let's compute divergence first. Divergence is conveniently symbolized by this dot product with the del operator. So we take this del operator and we dot it with our field. Now remember how that works. It's an operator. So everywhere you would typically multiply, you operate instead. We're going to take the partial of the x component with respect to x. And then the partial of the y component with respect to y. The derivative of this with respect to x, that's 3x squared, and y squared is a constant, so you bring that down. The derivative of this with respect to y, that's a constant times y. So we just get the constant. That's the divergence. And then we need bounds for r. So we just look at our region. We want one variable to go from a function to a function, the other one to go from a constant to a constant. We notice that if we draw our rectangles this way, y goes from a function to a function, and x goes from a constant to a constant. Y goes from the bottom function, which is the parabola, to that top function, which is a line. And I'm not going to do it in this video. But in order to find the bounds for x, you set the y value on this curve equal to the y value on that curve, and you solve the equations for x. So you're setting y1 equal to y2. You solve this. Eventually you get x equals 0 and x equals 2, so that we get that point of intersection and that point of intersection. And those give us bounds for x. Okay, so we got our bounds for y and x. And then we just substitute. And evaluate. So my flux integral is equal to the double integral over r of my divergence. And integrate with respect to y first and then x. And y goes from the parabola to y equals x, and x goes from 0 to 2. Okay. So we start on the inside, we work our way out. Integrate with respect to y first. So you bring the 3x squared down, then you add 1 to the exponent and divide by the new exponent. And this is constant. The antiderivative of the constant with respect to y is that constant times y. The 3's reduce. Evaluate from x squared minus x to x for y. So we'll have x squared times, when y is replaced with x, x cubed, that's x to the 5th, plus 1/4, x to the 4th times x, that's another x to the 5th. Okay, so that's at the upper bound. And then at the lower bound, we get this x squared times the quantity x squared minus x cubed. Ooh, it's a lot of algebra. It's okay. It's just tedious. And then we've got 1/4 x to the 4th times y, which is x squared minus x. And we integrate all of that with respect to x. No big deal, just a lot of distribution and power rules. Okay. So I've got 1 plus 1/4 is 5/4. X to the 5th right there. And over here, I could just write this out 3 times and distribute. That would be a pain. Instead, I'm going to do a little bit of factoring. I'll look at this and see that they both have an x squared minus x in common. So I'll factor that out. So I have minus x squared minus x times the quantity. What's left over here is an x squared times an x squared minus x quantity squared, plus a 1/4 x to the 4th. It didn't save us a lot of time. It saved us some. That'll be okay. So I'm going to review just a little bit less algebra here, so I don't take up too much of your time in Calculus 3 doing algebra. When I write this twice in FOIL, I get a trinomial. First times first will be x to the fourth. Outer times outer will be negative x cubed. Inner times inner will be the same, so we'll have two of them. Last times last will be an x squared. Now we can distribute the negative x squared to each of these guys. And you could simplify this. End up with this plus this is 5/4 x to the fourth. Okay, so tedious. Then we multiply, let's multiply through by this x squared and that negative x, but let's distribute the negative as well. So I'll have a negative x squared times that trinomial. And then I have a negative times a negative is a positive x times that trinomial. Distribute again. I know. Feels like it's been a while since I've done any calculus at this point. But truth is, you can't get the right answer to your calculus problem until you do all of the algebra correctly. So you don't want to say it's just algebra and it doesn't matter, because it matters a lot. Without the correct algebra, it's wrong. We want to be accurate, don't we? All right. Finally, I can collect like terms. Let's see. I've got a couple of x to the seventh terms, 2x to the seventh and x to the seventh. So that's 3x to the seventh. Oh, there was an x to the eighth. He's trying to put them in descending order. That's okay. Do I have any x to the sixth terms? I've got one here and then one there. So I have negative 5/4 of those, minus 2 of those. So minus 8/4 of those. So that's minus 13/4 of those. And the x to the fifths, we're going to have 10/4 or 5/2. Okay. Oops, got them all. All right, now it's just a Calc 1 antiderivative, one of the simplest kinds, just a power rule. So we add 1 to the exponent, divide by the new exponent. Add 1 to the exponent and divide. Bring that constant down. Add 1 to the exponent and divide by the new exponent. Bring that constant down. Add 1 to the exponent and divide. Evaluate at 0 and 2 and subtract. So we'll have 3/8 times 2 to the 8th minus 2 to the 9th over 9 plus 13/28 times 2 to the 7th plus 5/12 times 2 to the 6th. And then when x is 0, we get 0. So just do the arithmetic on my calculator. Okay, so we get 7,888 divided by 63. That's my exact answer, which is generally what I want, but I wanted to see kind of what it was. I got approximately 125.2. Okay, what does that represent again? Anybody remember what it was we were starting with? 125 over 2. That's right, they asked for flux, didn't they? This is what we were working on. And since we have Green's theorem, rather than evaluating this line integral, which involves parameterizing this, finding f as a function of t, finding x prime and y prime, and using those to construct that outward unit normal, and evaluating a definite integral for t between 0 and 2, and then maybe t between 2 and 4, and to get that line segment and then adding them together, we said instead of doing that, we can do this. And then we said, what does that mean exactly? And if you want to find the flux across C on the boundary, instead of doing that, you can find the flux or the divergence on each little area piece instead, and then add all of those together. What goes out of one rectangle will go into the other rectangle, except for the ones on the boundary. Those are the only ones that are going to contribute to the answer. And so the flux across the boundary is equal to the double integral of the divergence. In practice, all we had to do was calculate divergence, find a way to describe R, and then evaluate a double integral, which required a lot of algebra, but eventually it was just a Calc 1 integral, no big deal, and we get this number. This is flux. Is there more fluid going out of this region or into this region? Say out, because the flux is 125.2 approximately. Does that mean there's never any points on the curve where fluid is going in? No, that's not what it means. It means that after we took into consideration all the fluid moving out and all the fluid moving in, we added all of those up. Net, we had 125.2 units, of fluid moving out. We'll make sure that we understand exactly what those units are when we talk about the divergence theorem, which is the surface integral version of this for triple integrals. When we talk about surface integrals later. I think that's enough for this video. That's flux. This integral is equal to this integral, provided that these three conditions are satisfied.